Hi, welcome to our channel of IGNOU Audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Certificate Programs Postgraduate Certificate. Advanced Certificate in Power Distribution Management, ACPDM. B00 to Energy Management and IT Applications. Block-1 Energy Conservation, Audit and Accounting. Unit-1 Energy Conservation. 1.1 Introduction. Energy is essential to life and the key to human progress. Its conservation is essential in the modern industrial societies. The reasons are many. Coal and other fossil fuels are likely to be depleted soon because once consumed, they are no longer available to us in the same form. Today, 85% of the primary energy comes from fossil fuels. Their reserves are finite and will not exist for future generations as the consumption increases with increasing population. You will agree that considerable wastage of energy is taking place in our country. We have to learn to use the energy resources judiciously to avoid energy death for our future generations. For this, we need to understand what energy resources are available to us and for how long. How can we make them last longer? Energy conservation becomes important in this context. We begin this course by discussing energy conservation in general and then, with special reference to the electricity sector, we discuss related concerns and issues such as times the impact of energy production and consumption on the environment, times the importance of improving energy efficiency, times ensuring energy security for all, and times exploring sustainable energy options for future. We present examples and case studies of how people around the world are grappling with these issues. We begin by exploring the energy resource base of our planet Earth with special reference to India. 1.2 Earth's energy resource base. In this section, we address the following questions. What are the energy resources available to us? How fast are these being used up? How long will these last at the present rate of consumption? Let us take them up one by one. What energy resources are available to us? The sun is the principal source of energy on our planet. Other common sources of energy are fossil fuels like coal, oil, natural gas, biomass, such as wood, agricultural waste, etc., water, wind, and nuclear energy. Some uncommon energy sources include geothermal energy and tidal energy. These energy resources are usually classified as primary and secondary resources, renewable and non-renewable resources, and commercial and non-commercial resources. Primary and secondary resources. Primary energy resources are those that are found in nature. These are mostly converted into secondary resources in industrial utilities. For example, coal, oil and gas, primary energy resources, are converted into steam and electricity, secondary resources of energy. Renewable and non-renewable resources. The energy resources such as coal, oil and gas cannot be replenished and are likely to be depleted with time. These are known as non-renewable resources of energy. Their supplies are limited, and when these supplies are over, we will not be able to use these resources. On the other hand, hydro energy, wind energy, biomass energy, solar energy, tidal and geothermal energy are renewable resources of energy. These can be replenished in a short period of time. So these resources will not be depleted if they are managed properly. Commercial and non-commercial resources. The energy resources that are available in the market for a definite price are known as commercial energy resources. These include coal, oil, natural gas, electricity, and refined petroleum products. There are certain energy resources that are not available in the commercial market for a price. These are called non-commercial energy resources. For example, cattle dung, agricultural wastes, solar energy for drying food products, animal power for transport, threshing, lifting water, etc., are not bought or sold at a price. These are also called traditional fuels. As far as the electricity sector is concerned, you know that the major resources for generating electricity in our country are coal, oil, natural gas, and hydropower. Nuclear energy and renewable energy resources together provide only 8% of the total power produced in India, Fig. 1.1. Thus, at the moment, we shall talk only about the resource base comprising coal, oil, and gas. Let us now look at the other questions. How fast are the energy resources being used up? How long will these last at current rates of consumption? To answer these questions, we need to understand another term called the reserve production (RP) ratio. It is often used as a quick way of indicating how long current reserves will last at current production rates. See note in the margin. For the purpose of estimating resource availability, we also classify the energy resource base into three categories. A. Proven, found and ready to be produced. B. Probable, expected to become proven in due course of time. C. Speculative, estimated but uneconomical for extraction. Entrepreneurial drive and development of new technology can turn the energy resource base times from probable into proven, and times from speculative into probable. In this way, the life of the energy resource base can be extended for many more years. In fact, we can use an interesting insight from history and be optimistic about our energy future. Still, we need to use our resources judiciously to make them last longer. How much longer can we make them last? This will depend on the resources available to us now and their rate of production and consumption. Let us look at the findings of the World Energy Council Survey 2004 about this issue. Study the table given below. Table 1.1 RP ratios for coal, oil and natural gas for the world. What does the data in this table tell us? For example, the current world coal reserves are about 909 gigatons. Dividing this number by the current production rate of about 4.8 gt per year, we obtain an RP ratio of about 200 years. This is the origin of the statement we have about 200 years of coal left. What is the situation for oil and natural gas? The information is summed up below for the entire world. Oil 40 years. Natural gas 60 years. Coal 200 years. The RP ratio has limitations as an indicator of how long a reserve will last, since it neglects the effects of growth in demand due to increase in population and consumption. But it also neglects the effect of growth in reserves. Growth in reserves occurs as previously uneconomical deposits can be harnessed by improved technology. Still, it is a useful concept for reducing a large number of a resource reserve to an understandable scale. Don't you think that this statement is easier to understand? We have 200 years of coal left at current mining rates than this one. We have 200 billion short tons of coal reserves. In that sense, the RP ratio is a useful tool. In Table 1.2, we have given similar data for India. Study the table and answer SUC 2. Table 1.2, RP ratios for coal, oil and natural gas for India. Although India has huge coal reserves, it cannot use them as they tend to have high ash content and low calorific value, Fig. 1.2, due to the low quality of much, 73% of its coal, India has to import sizable quantities of coal for power generation. Data in Table 1.2 tells us that the oil and gas reserves of India are not going to last very long at current rates of consumption. As it is, we rely on substantial imports of oil and gas. Keeping in view the price rise, the volatility and the instability of the oil and gas markets, we must focus our efforts on energy conservation with renewed vigor. Fossil fuels continue to dominate energy use worldwide due to high oil and natural gas prices. Coal consumption continues to exceed oil and natural gas consumption in the world. The largest increases in coal use are projected for China and India at 70% of the total world increase in coal demand. You have learnt that energy conservation is needed for conserving energy resources and making them last longer. It is also necessary because the energy technologies and consumption of energy are taking a heavy toll on the environment. You can play an important role in this respect and should study about the need for energy conservation in this context. 1.3 Energy conservation, issues and concerns. As the population in our country grows and the pace of urbanization increases, energy use is bound to increase. Moreover, as our wealth grows, energy use per capita will also increase. At present, India is the fifth largest consumer of energy in the world. However, our per capita energy consumption is very low. In order to increase the available supply of energy, we need to reduce the total demand for energy as well as slow the growth in energy consumption. At the same time, we need to ensure energy security for all. In this context, we can say that energy conservation is a practice for Black Diamond ensuring judicial usage of energy and Black Diamond decreasing the quantity of energy consumed while achieving a similar outcome of end use. The motivations for energy conservation could be different for individual, commercial and industrial users. Direct consumers of energy such as individuals or organizations may want to conserve energy to reduce energy costs and protect the environment. Increase in efficiency and maximizing profits could be the motivation for industrial and commercial users to save energy. Energy conservation can be a result of several processes or developments, such as increase in productivity, technological progress resulting in more energy-efficient technologies, and most importantly a positive attitude towards efficient energy usage. For example, suppose the energy end use is to keep a room cool in summers. Energy conservation efforts would look at Black Diamond better technology options, such as sensors to switch off the devices, films on windows, better insulation or solar passive building, etc. Black Diamond reducing wasteful use of energy and increasing energy efficiency of the appliances being used, and Black Diamond increasing consumer awareness for reducing energy consumption. Energy conservation is cheaper and more environmentally benign compared to increased energy production. We need to encourage it amongst all categories of consumers. You will appreciate this point better once you study about the impact of energy production and use on the environment. 1.3.1 Energy and Environment. Many major environmental problems we face today are linked with the energy sector. To a large extent, the energy production technologies and energy use are responsible for greenhouse gas emissions, global warming, and the consequent climate change. Environmental pollution, particularly in urban areas, is a major concern today. Environmental degradation due to deforestation is one of the major consequences of developmental activities and the quest for cheaper sources of energy in the developing world. We now discuss these issues briefly. Global warming and climate change. This is a major global environmental concern today, with profound implications for the way the world produces and consumes energy. It is now an accepted reality that global warming is taking place due to the enhanced greenhouse effect, Fig. 1.3. Energy-related human activities are leading to excessive concentration of greenhouse gases, GHGs, such as carbon dioxide, methane, water vapor, nitrous oxide, ozone, chlorofluorocarbons, CFC, halogens, and peroxyacetylnitrate, PAN, in the Earth's atmosphere. These gases trap the heat reflected from the Earth's surface and do not allow it to escape into space. This increases the temperature of the atmosphere. In trace amounts, gases like coal to make the Earth warm enough to sustain life. This is the natural greenhouse effect. In excessive amounts, these gases can be very harmful, as you will learn in this section. Figure 1.3, the greenhouse effect, explained in the box. The greenhouse effect is enhanced due to human habitations and various human activities, particularly in the industrialized countries. More than two-thirds of the world's GHG emissions originate from the energy sector in processes like energy production and energy end use in various sectors, such as industry, transport, agriculture, power sector, etc. Other sources include activities in residential and commercial areas, energy production technologies like thermal power plants, and the combustion of fuels in various activities like cooking, heating, transport, industries, etc. Add greenhouse gases to the environment. It is now well established that the increasing greenhouse gases will cause the Earth to warm so fast that we may not be able to adapt to the resulting changes. It is estimated that the global temperature will increase by another 1.5 to 4.5 degrees Celsius sometime in this century if we do not take drastic measures. Some scientists have started referring to global warming as global heating. This is meant to be a wake-up call for the world. Can you imagine what can happen due to this kind of heating up of the atmosphere? It is predicted that polar ice caps will melt and glaciers will retreat. Low-lying lands and coastal areas will be submerged in water. Extreme weather events such as droughts, floods, hurricanes, tornadoes, heat waves would increase. And all this could happen within our lifetime. Since less energy use leads to less energy production, energy conservation indirectly restricts the production of greenhouse gases, and therein lies its importance. We can all reduce wasteful use of energy and prevent global warming by reducing greenhouse gas emissions due to our activities. Otherwise, we could face severe deterioration of civilization. Environmental pollution. Every stage of energy usage, from extraction of an energy resource to its transportation and end use, leads to environmental pollution. For example, Extraction of coal degrades the local habitat through dust in the air, groundwater degradation, and solid waste generation. Similarly, the local environment is polluted highly due to oil extraction and controlled venting is required to manage the production. We now briefly discuss the air, water and land pollution due to various energy activities. Air pollution. Several hazardous air pollutants apart from GHGs are emitted in energy-related activities. Fossil fuel combustion produces smoke and noxious gases such as sulfur dioxide, nitrous oxide, and carbon monoxide, as well as particulates like fly ash and soot. These are the major atmospheric pollutants. Other air pollutants and their sources in the energy sector are shown in Fig. 1.6. You may like to record the contribution of energy production and its use to air pollution. Air pollutants cause many health problems, particularly amongst children, the elderly people, and those with respiratory diseases. These can even be fatal as reported in several studies. Ingestion of heavy metal pollutants, including lead, arsenic, and mercury from the burning of coal and oil can even cause cancer. These effects can be mitigated by times limiting people's exposure to the pollutants, times appropriate siting of the power producing plants as well as large energy consuming facilities like industrial plants, times installation of pollution control devices on polluting industries and vehicles, and times enforcement of stringent emission regulations and air quality norms. Fig. 1.6. Air pollutants and their sources in the energy sector. We now know that approximately 2/3 of the deaths due to fine particle pollution from power plants could be avoided by reducing their sulfur dioxide and nitrogen oxide emissions by 75% below the 1997 emission levels. However, some of the polluting byproducts can be put to good use. For example, fly ash is being used to make construction materials like bricks, tiles, etc. Water and land pollution. The main sources of water pollution from the energy sector include times waste and chemical deposition from the outcome of energy production conversion process, times hot water discharge from thermal power plants, known as thermal pollution, times runoffs from mining sites, times acid rain, and times leakage during transportation of oil through water, which can destroy the local marine life. Thermal pollution can affect the natural balance of ecosystems in the water body. Water at temperatures higher than 35 degrees Celsius does not contain enough oxygen for aquatic life. New thermal power plants are built with permanent cooling towers, which use evaporation to cool water. All or part of the hot water can be pumped through cooling towers to lower the temperature before it is released into the water body. Acid rain is caused when the burning of fossil fuels emits sulfur dioxide into the atmosphere. The sulfur dioxide reacts with the water in the atmosphere, creating rainfall which contains sulfuric acid. As acid rain falls into lakes, streams, and ponds, it can lower the overall pH of these water bodies, killing vital plant life in them. This affects the entire food chain. Less vegetation leads to further oxygen imbalance in the atmosphere. This vicious circle adversely affects life on our planet. Acid rain can also leach heavy metals from the soil into the water, killing fish and other aquatic organisms. Land and soil pollution problems due to the energy sector arise mainly from siting and waste disposal. All energy-related activities have some Sort of siting impact. In this context, mining sites and hydroelectric reservoirs have attracted maximum attention. Fuel refining and other electric power plants too involve large facilities or complex industrial processes. Water and soil can become contaminated with toxic materials from energy-related industries, mine sites and abandoned hazardous waste sites. This can of course be taken care of by following stringent norms for waste disposal at suitably chosen sites, especially hazardous waste disposal of radioactive waste containing long-lived radionuclides, in particular. Siting problems also occur for installing transmission lines and electric substations. The effects of electromagnetic fields associated with transmission voltages up to 800 kV on humans and animals are under investigation. Nuclear energy is being projected as a clean source of energy, but even this energy option has its problems, such as radioactive waste disposal, threat to health from nuclear radiations, and the fearsome possibility of nuclear accidents, and the stockpiling and proliferation of nuclear weapons. These problems can be tackled to a large extent if we enforce strictly the laws for preventing environmental pollution. So far, you have studied about energy resource availability and the impact of energy production and end use on the environment. Are you not convinced by now that we need to promote all possible measures for energy conservation? The next logical question is, how can we do it? We can adopt the following strategies for environmental management to contain the negative impact of power sector on the environment. Strategies for environmental management in the power sector. Black diamond. Since hydropower is a cleaner source of power, there should be a greater thrust on its development in the short, medium, and long terms. Hydropower would reduce carbon dioxide and other GHG emissions. Black diamond for thermal power generation, the cleanest fuel economically available, should be chosen. Natural gas is preferable to coal subject to its availability and price. Clean coal technologies could be promoted in the short term, especially coal beneficiation could be undertaken in the short term to achieve immediate benefits. Other clean technologies like supercritical boilers and integrated gasification combined cycle, etc., could be promoted in the long term. Preference needs to be given to high heat content, low ash, low sulfur coal, and beneficiation should be considered for high ash coal. Black diamond fly ash management and utilization through suitable market-based instruments should be facilitated. The fly ash should be priced appropriately. Public acceptance of fly ash-based products could be improved through awareness and demonstration. Movement of ash through the rail network should be facilitated. Black diamond exploitation of coal bed methane as a clean alternative source of energy could be adopted. Black diamond. There should be a greater thrust on renewable resources of energy, and these should be developed as decentralized sources of energy. The thrust of the discussion so far is use clean energy and conserve it. You could coin your own slogans conveying this message. Another way of conserving energy resources is to reduce the energy intensity of our economy by improving the energy efficiency in the power sector. 1.3.2 Improving energy efficiency. All countries with growing economies can dramatically reduce growth in energy use by reducing energy intensity and improving energy efficiency. They can bring about reductions in emissions of polluting gases, including greenhouse gases, particularly by shifting to cleaner sources of energy, such as natural gas and renewable energy resources. Let us begin by Understanding the concept of energy intensity. Energy intensity. Energy intensity is defined as the ratio of energy consumption to the gross domestic product, GDP. It is calculated as units of energy per unit of GDP. Energy intensity is a measure of the energy efficiency of a nation's economy. High energy intensities indicate a high price or cost of converting energy into GDP. Low energy intensity indicates a lower price or cost of converting energy into GDP. Below a certain level of development, growth results in increase in energy intensity. With further growth in economy, the energy intensity starts declining. In 2001, India's energy intensity, energy consumption per dollar of GDP, figured in the highest bracket in Asia, surpassed only by Pakistan and China. However, in terms of purchasing power parity, the energy intensity of India is lower than that of USA and the world average, as the table below indicates. World average 0.21, OECD 0.19, USA 0.22, Australia 0.20, India 0.19, China 0.23. Many factors such as the general standards of living and weather conditions influence an economy's overall energy intensity. For example, a nation with extreme weather conditions requiring heating and cooling, long commutes, and extensive use of generally poor fuel economy vehicles will have high energy intensity. In comparison, a nation that has mild and temperate weather, demographic patterns of workplaces close to home, uses fuel-efficient vehicles, supports carpools, mass transportation, or walks or rides bicycles, will have low energy intensity. Note, WTO and increasing global trade will wipe out Indian goods if the energy intensity is not lowered to a level that competes well with both developed and developing countries. We now discuss how improving energy efficiency helps in the goals of reducing energy intensity and conserving energy. Power system energy efficiency significantly depends on making optimum choices about fuels, technology, scale of operations, energy pricing, design of buildings, habitats and transportation systems, and the standards for energy end-use applications. Thus, we can say that energy efficiency in the power sector has two dimensions: supply-side efficiency in energy conversion to its cleanest form, conversion to electricity, and demand-side efficiency in end usage. Note that electricity generation involves conversion of mechanical, chemical or nuclear energy into electrical energy. Refer to Unit 2. Conversion of mechanical energy to electrical energy occurs at a higher efficiency. Maximum loss occurs during the conversion of chemical energy to thermal energy. We now briefly discuss the aspects of supply-side efficiency and demand-side efficiency. Supply-side efficiency. Increasing efficiency in energy conversion to electricity has to be carried out at the levels of generation, transmission, and distribution. In India, the overall efficiency for the coal-based power plants ranges from 28% to 35% depending upon the size, operational practices, and capacity utilization. After generation at the plant, electricity is transmitted and distributed over a wide network. The primary function of transmission and distribution equipment is to transfer power economically and efficiently from one location to another. Conductors in the form of wires and cables strung on towers and poles carry the high voltage and current. Energy loss in transmission lines occurs in the form of heat losses. The power transmission and distribution system has many other components like capacitors, switches, relays, circuit breakers, and fuses. Transformers are placed at strategic locations throughout the system to minimize power losses in the Tandy system. They are used to change the voltage level from low to high in step-up transformers and high to low in step-down units, Fig. 1.10. You may like to know what the energy efficiency is as electricity is transmitted from the power source to the end user. It is 87%. Thus, the technical losses are of the order of only 13%. In India, the standard technical losses are around 17%, which implies an efficiency of 83%. However, in the case of industrial users, the overall energy efficiency is 50%. This is because at the user's premises, there is a network of transformers, motors, substations, pumps, flow control valves, throttling, etc., which further reduce the energy efficiency. Hence, 1 unit saved by the end use is equal to 2 units generated at the power plant. If you want to go into the technical aspects of supply-side energy efficiency, you may like to read the information given in the box below. You may skip it if you are not technically inclined. Demand-side efficiency. Demand-side efficiency can be managed with energy-efficient end usage. Around 2/3 of the energy is lost while converting primary, secondary and final energy into useful energy services. Improving the energy efficiency of end-use applications would further help in energy conservation. Although we will discuss this issue in detail in Units 4 and 5 of this block, we would like to set the tone of the discussion right here. The Indian consumer market is extremely price-sensitive. Consumers prefer lower initial capital outlay to optimization of life cycle costs. A case in point is the lower efficiency of rewound motors, which constitute nearly 50% of the capital stock in the low and medium capacity range. This is where the implementation of compulsory energy efficiency standards can promote energy-efficient options. Minimum energy efficiency standards need to be formulated and rigorously implemented for moving the users and the market in the direction of efficient energy use. The development of compulsory energy efficiency standards for end-use applications by the Bureau of Energy Efficiency should be able to bring this about. Industries require heating, cooling, rotating machines, shop floor, lighting, etc. Necessary measures can be taken to minimize heat loss. Use energy-efficient rotating machines and lamps. These will not reduce the effectiveness of the processes, but will definitely reduce energy consumption. Liberalization and competition, as in the cement industry, coupled with proactive and focused schemes for upgrading technology and development, as in the sugar industry, have worked well in improving the energy efficiency of the Indian industry. In fact, industries today are going in for retrofitting energy-efficient equipments to reduce the cost of extra energy consumption. Right from using energy-efficient lamps to energy-efficient motors to getting energy audits done, many industries are successfully saving on their energy bills. You can go through the case study given below to appreciate what can be done by an industry to improve energy efficiency. This case study is taken from the report on Industrial Technologies Program, Energy Efficiency and Renewable Energy, U.S. Department of Energy, Washington, D.C. Little thought has been given to the planning and layout of urban habitations in India with a view to reduce the energy demand made by civic amenities and the transportation sector. We need to maximize public transportation facilities as opposed to private transportation. Although car manufacturers are developing more and more energy-efficient vehicles to minimize the resource usage, stress should be laid on minimizing fuel usage or making it more efficient. Similarly, higher levels of electrification in the railways can increase their energy efficiency. These, however, are system-wide changes that can be implemented only if the concept of energy efficiency is integrated into town planning and architecture. While technology is trying to cope up with the growth rate of population and demand for energy, it is the individual consumer's behavioral pattern that can drastically reduce energy consumption. For example, we can save energy by taking simple steps such as carpools to travel to office or CFLs, Box 1.1, 2. Light our homes. We shall talk about these aspects in Unit 5 in detail. Box 1.1, Characteristics of Compact Fluorescent Lights, CFLs. CFLs are efficient. CFLs are 4 times more efficient and last up to 10 times longer than incandescent bulbs. A 22-watt CFL has about the same light output as a 100-watt incandescent bulb. CFLs use 50 to 80% less energy than incandescent bulbs. Less expensive, although initially more expensive, you save money in the long run because CFLs use 1/3 RD the electricity and last up to 10 times as long as the incandescent bulbs. Reduce air and water pollution. A single incandescent bulb replaced with a CFL will keep half a ton of carbon dioxide out of the atmosphere over its lifetime. Non-commercial energy resources continue to be the dominant fuel used by the urban poor and in rural areas, and this accounts for around 42% of the energy losses. Improvement in energy efficiency in this area has significant equity considerations. The energy efficiency of non-commercial energy resources in traditional applications is less than 10%. This can be doubled by gasification and by imposed end-use applications. Technology to extract these efficiencies is being developed. However, implementation is slow. Non-commercial energy resources can be commercialized into decentralized energy systems that are accessible to the local people, are technologically relatively unsophisticated, and can be locally managed. However, we would need to improve the efficiency with which locally available natural resources are used to provide energy to rural users. Energy is the lifeline of modern societies. Today, India has 17% of the world's population, but its per capita energy consumption is one of the lowest. In fact, the energy distribution between developed and developing countries is highly skewed in favor of the former. We would like you to understand this gap to be able to envision the future mission of the power sector. Energy distribution between developed and developing countries. Although 80% of the world's population lives in the developing countries, a fourfold population increase in the past 25 years, their energy consumption amounts to only 40% of the world's total energy consumption. The world average energy consumption per person is equivalent to 2.2 tons of coal. In industrialized countries, people use 4 to 5 times more than the world average and 9 times more than the average for the developing countries. An American citizen uses 32 times more commercial energy than an Indian citizen. Energy consumption is integrally linked with the quality of life and per capita. Energy consumption is regarded as an indicator for human development. Today, the high standards of living in the developed countries can be attributed to their high energy consumption levels. The rapid population growth in the developing countries may be regarded as one reason for low per capita energy consumption. However, we must ensure good quality energy supply to all our citizens at affordable costs at all times. Ensuring energy security for all is a very important goal for our country, and the power sector has tremendous responsibility on its shoulders in attaining it. Let us try to understand its implications and the options before our country. 1.3.3 Ensuring energy security for all. The basic aim of energy security for a nation is to provide sufficient energy for all while reducing its dependence on the imported energy sources for its economic growth. Energy security rests on two principles. Times to secure access to all sources of energy including coal, oil and gas. Supplies within the country and worldwide till the end of the fossil fuel era, which is fast approaching. Simultaneously, we should access technologies to provide a diverse supply of reliable, affordable, and environmentally sustainable energy. Times to use the least amount of energy to provide services and cut down energy losses. We need to be energy secure in terms of energy resource, i.e., where it comes from, control of the flow and distribution of the resource, and should have alternatives in place to allow us to withstand the highs and lows associated with any commodity. As far as the energy security of India is concerned, you should know that our country has just 0.8% of the world's known oil and natural gas resources. Since 1985, our country has been a net importer of coal. It has been unable to raise oil production substantially in the past few decades. Rising oil demand of close to 10% per year has led to sizable oil import bills. The dependence of energy imports is projected to increase in the future. This energy import dependence implies vulnerability to external price shocks and supply fluctuations, which threaten the energy security of the country. Increasing dependence on oil imports means reliance on imports from the Middle East, a region susceptible to disturbances and consequent disruptions of all supplies. This calls for diversification of sources of oil imports. The need to deal with oil price fluctuations also necessitates measures to be taken to reduce the oil dependence of the economy, possibly through fiscal measures to reduce demand, and by developing alternatives to oil, such as natural gas and renewable energy. India will continue to experience an energy supply shortfall in the foreseeable future unless adequate measures are taken forthwith. Energy security can only be ensured by a shift in the structure of energy sources. We would need to minimize fossil fuel imports and assure secure access to energy resources. Some of the strategies that can be used to meet the future challenges related to our energy security are times building stockpiles, times diversification of energy fuel sources, times increased capacity of fuel switching, times demand restraint, times development of renewable energy sources, times improving energy efficiency, and times sustainable development. Although all these options are feasible, their implementation will take time. Also, for countries like India, reliance on stockpiles would tend to be slow because of resource constraints. Besides, the market is not sophisticated Enough or the monitoring agencies experienced enough to predict the supply situation in time to take necessary action. Insufficient storage capacity is another cause for worry and needs to be augmented if India has to increase its energy stockpile. We should tap the hydro and nuclear power potential to the maximum. Further, targets for power generated through renewable energy technologies may be raised to 20 or 25% against the present 5%. Distributed generation (DG) technology is the latest concept for meeting local requirement with local resources at the remotest location with clean form of energy. Microhydro, biomass, solar energy are some of the resources used for DG. These measures would also lead to sustainable energy use in future. As we near the end of this unit, you may like to know what are the future energy options available to us for ensuring energy security and sustainable use of energy. We have two main options for the delivery of sustainable energy to the consumer. Black diamond, the favored and more convenient option, is to maintain the chemical energy base. This would mean replacing fossil fuels by synthetic hydrogen and continuing the energy business as usual. In this scenario, oil companies would become hydrogen suppliers, roadside fueling stations would pump hydrogen instead of gasoline, and cars would be powered by hydrogen and fuel cells. This option, termed hydrogen economy, can certainly be realized. The necessary technology is available or can be developed in time. The second option is a controlled transition from the chemical energy base to an electrical energy base. Renewable energy can be brought to the people in the form of electricity. The necessary technology is also available or can be developed rapidly. This option, termed an electron economy, can certainly be realized. Both these options deliver renewable electricity to the people, but through different energy carriers and require additional research and development. New storage technologies are needed for hydrogen as well as for electrons. But a hydrogen infrastructure must be built from scratch. In simple terms, a hydrogen economy has to compete with an electron economy. The option with the lower energy losses between energy source and energy services would be preferred. This situation is illustrated in Fig. 1.13. The competition between hydrogen and electricity will be determined by the respective overall energy efficiency between renewable source and end use. Fig. 1.13. Energy distribution options in a sustainable energy future. However, of all these options, the simplest and the most easily attainable is reducing demand through persistent energy conservation efforts. In the light of the discussion so far, we can outline an energy strategy for the future with immediate, medium-term and long-term goals. 1.3.4 Energy Strategy for the Future. We list below the various elements of the immediate, medium-term and long-term energy strategy. Immediate strategy: rationalizing the tariff structure of various energy products. Optimum utilization of existing assets. Efficiency in production systems and reduction in distribution losses, including those in traditional energy sources. Promoting R&D, transfer and use of technologies and practices for environmentally sound energy systems, including new and renewable energy sources. Medium-term strategy: demand management through greater conservation of energy, optimum fuel mix, structural changes in the economy, and appropriate model mix in the transport sector, i.e., greater dependence on rail than on road for the movement of goods and passenger, and a shift away from private modes to Public modes for passenger transport, railroad coordination, changes in design of different products to reduce the material intensity of those products, recycling, etc. A shift to less energy-intensive modes of transport. This would include measures to improve the transport infrastructure, viz., roads, better design of vehicles, use of compressed natural gas, CNG, and synthetic fuel, etc. Similarly, better urban planning would also reduce the demand for energy use in the transport sector. A shift away from non-renewable towards renewable energy sources, viz., solar, wind, small hydro, biomass energy, etc. Long-term strategy. Efficient generation of energy resources times efficient production of coal, oil and natural gas times reduction of natural gas flaring times clean coal technology, improving energy infrastructure times building new refineries times creation of urban gas transmission and distribution network times maximizing efficiency of rail transport of coal times building new coal and gas-fired power stations, enhancing energy efficiency times improving energy efficiency in accordance with national, socio-economic, and environmental priorities times promotion of energy efficiency and emission standards times labeling programs for products and adoption of energy-efficient technologies in large industries, deregulation and privatization of energy sector times reducing cross-subsidies on oil products and electricity tariffs times decontrolling coal prices and making natural gas prices competitive times privatization of oil, coal and power sectors for improved efficiency, investment legislation to attract foreign investments times streamlining the approval process for attracting private sector participation in power generation, transmission and distribution. At this point, we would like to end the discussion and summarize what you have studied in the Unit 1.4 summary. The main concepts covered in this unit are as follows. Times the Earth's energy resource base comprises the Sun's energy as the principal source of energy on our planet, fossil fuels like coal, oil, natural gas, biomass, such as wood, agricultural waste, etc., and water, wind, nuclear energy, geothermal energy and tidal energy. Of these, coal, oil, natural gas and hydropower are the major resources for generating electricity in our country. These resources can be classified as primary and secondary, renewable and non-renewable, and commercial and non-commercial. Times the reserve production, RP, ratio for each type of energy resources obtained by dividing its reserves remaining at the end of the year by its production in that year. It tells us how long these resources would last at the present rates of production and consumption. For India, the coal, oil and natural gas reserves are expected to last for over 250 years, 20 years and 28 years, respectively. Times in view of the depleting energy resources and the adverse impact of energy production and usage on the environment, energy conservation is advocated as a practice for ensuring judicious usage of energy and decreasing the quantity of energy consumed while achieving a similar outcome of end use. Times some of the adverse environmental effects of energy-related activities include global warming and climate change due to the increase in greenhouse gases in the environment and air, water and land pollution. Times improving energy efficiency in both supply and demand sides is a key to energy conservation without compromising the quality of life in a society which has energy as its lifeline. This, coupled with the use of environment-friendly energy options, forms the cornerstone of a sustainable energy future. Times ensuring energy security for all is a very important goal for our country. The basic aim of energy security for a nation is to provide sufficient energy for all while reducing its dependence on the imported energy sources for its economic growth. For this, we need to secure access to all sources of energy as well as access technologies to provide a diverse supply of reliable, affordable, and environmentally sustainable energy. We also need to use the least amount of energy to provide services and cut down energy losses. Times our energy strategy should have immediate, medium-term, and long-term goals to meet our energy needs at affordable costs, both economic and environmental. Energy conservation efforts would form the cornerstone of the energy strategy. Thank you. Subscribe to our channel.